Good afternoon and welcome to Carl and Cymru revision sessions. This session will focus on work done and energy transfer for GCSE Year 11 Physics, and it will be presented by Mrs. Owen from Penglais School. The session will last around 45 minutes where the teacher will go through any relevant subject content. If you have any questions, please use the question and answer section and we will endeavour to answer your question during the session. The session will be recorded with the recording and any relevant resources uploaded to the e-sgol website in the Carl and Cymru area. Diolch. All right, and without any more delay, over to you, Mrs. Owen.
Okay, thank you very much, Mr. Ridd. And yes, we will be doing energy transfers and work done. And I've lifted all of these definitions from the digital bank, the digital resources on the WJEC website. And before I go over those resources, what I would like to do is just show you a clip and talk you through the definitions that we are going to be looking at. Okay, so I want to show you this little clip of a Japanese entrance into, it's not worked again, has it, earlier this year, and I'll take that off. There we go. So what we are doing is we're looking at work done, force times distance. We are going to look at different types of energy. So the fact that he was moving quite fast in the middle of that half pipe, he had kinetic energy, and the fact that he used that kinetic then to be able to get to a really high height means that some of that kinetic energy is converted into gravitational potential energy. And then also he's slowing down as he's going along with his snowboard, so he's doing work against resistive forces such as friction. So before we dive into physics problems, we need to just go over all the terminology, the words that we use in physics, and the definitions and the equations that we use. So when a force acts on a moving body, we say that energy is transferred. And so we say that the energy transferred is known as the work done. This is really important because we have to look at the energy of the whole of the system, because energy cannot be created nor destroyed, but it can be changed from one form into another. So looking at work done is force times distance moved in the direction of the force, and that's quite simply this nice little equation: work done equals force times distance, FD. And we can interchange that with saying sometimes energy transferred, maybe it's turning into heat energy because you're doing work against air resistance or friction. You have to always look at what you're doing work against. What's that force? So an object can possess energy because of its motion, so that's your kinetic energy. So kinetic energy is given by half mass times velocity squared. Sometimes it's easier to put the half at the beginning, so you end up doing half of the mass times by the velocity squared. So we'll have to remember this equation. Now, if you're doing foundation, you don't have to remember this equation or use it. But if you do for the work done and energy transfer. The other sort of energy that we look at is gravitational potential energy by virtue of its height. So if something is set at a height above another reference place, and you can see that there's a height involved, then we look at potential energy. Now, very often we put gravitational potential energy is mass times gravitational field strength, which they'll always give you in the equation, in the question, say 10 newtons per kilogram. But if you ever progress to do A-level physics, this will be 9.81. But at GCSE, it will be rounded to 10. times by the change in height. Now, very often the change in height is given as a triangle. So we often talk about the change in the gravitational potential energy being the mass times gravitational field strength times by the change in the height. The other source of energy that we kind of like look at is deformation or elastic energy. So work done deforming an object, or the elastic energy stored in a spring or a rubber band. And that is given at GCSE as work done in storing the energy into the spring by stretching it or compressing it is given by half the force times by the extension. There is another equation for that, but that is all you need at this level. Now, it's worth reminding you that all of these kind of energies can be in a particular problem interchangeable, so that the total energy of the system remains constant. So energy can't be created nor destroyed, just change from one form into another. And you always have to be looking at what kind of energy has it got at the start, what kind of energy has it got kind of like at the end, and how that energy kind of like is very fluid in changing from one form to another. Now, if we are doing work against a resistive force, then we have to look at things like friction. So we say that the energy transferred is converted into doing work against the resistive force, i.e. friction. And so it turns into, very often, friction. All right, and you only have to see that because if you just rub your hands together, you've got your friction of your two hands, and that produces heat energy. But WJC refer to it as thermal energy, but the total energy of the whole system remains the same. But very often we say that if you're doing work against these resistive forces, it is dissipative, i.e. it goes out and you can't reclaim it, you can't get it back. All right, but it's not the fact that it's destroyed or anything like that. Okay, so let's have a look at the situation, you know, a simpler model than what you saw with the half pipe snowboarder, and have a look at a few questions dealing with these energy changes and work done. Okay, so there's a mass of a child, 40 kilograms at A, and so that climbs up to B at the top. So A has obviously been using some of her chemical energy, she's eaten some breakfast and got to the top. Now, the very fact that it's at a height above the reference point, which is the ground here, means that that little girl at the top has got gravitational potential energy. In fact, here, and it's always worth kind of like ringing all of your numbers in your question so that you've got them to refer to and you don't miss them in the text. So this gravitational potential energy here is 1,200 joules. All right, and we've been told that 55% of this energy is lost to the surroundings in sliding down, and this distance all along the slide here, not the height, is 12 meters, and that's all the information that we've got. And we've also got G is 10. They've given it to you. All right. So just have a look at the problem and set the scene. Okay, so this person has got gravitational potential energy at the top, and it will have kinetic energy at the bottom. And you've been told that the energy is being lost to the surroundings. So all of that gravitational potential energy at the start is converted into kinetic energy at the bottom plus energy lost to the surroundings. And I think once you've got in your head what is happening in terms of energy conservation, you can kind of like relate one part of the energy to another. So it says here, use an equation. So do use an equation to calculate the height. Now, you've been given the gravitational potential energy. you've been given the mass, you've been given the G10, and you have to work out the change in height. So that's what we want to do. So 1,200 equals 40 times by 10 times by the change in height. So rearrange that. 1,200 divided by 40 times 10 equals the change in height. So 12 divided by 4, and so the change in height is 3 meters. Now that looks about right, 3 meters high. Pop it into the answer line and move on. Now, given that you've sorted out what the energy changes are, calculate the kinetic energy of the child at sea. Well, I don't have the velocity, all right? I have the mass, so I can't just jump to kinetic energy equals half mv squared here. And nor does it ask you to use an equation. So perhaps we might have to use that equation further down. But you're going to have to use this idea of that energy is conserved and converted from one form into another for the next part. So you have been told that 55% of the energy is lost to the surroundings. 100% is what we started with initially. So that means that 100% was the gravitational potential energy, and that's going to be converted into kinetic energy at the bottom and the energy lost to the surroundings. So that means the kinetic energy at the bottom will represent 45%, because energy cannot be created nor destroyed. So 45 plus 55% will make your 100% is what you had initially. So if you work out what 45% of 1,200, then you will get the kinetic energy. So you can do it another way. You could work out 55% to get the energy lost to the surroundings and take it away then from your 1,200. That's fine. That's equally doable. Now, to work out 45%, divide it by 100 to give you the 1%, and then just times it by 45. Or you just do a ratio of 45 over 100. You might be more familiar with that approach. Okay, and that answer comes out as 540, so pop it in. And then from the kinetic energy that you've got, you can then slot it into kinetic energy equals half mv squared. So kinetic energy is 540 equals half of the mass is 40 kilograms times by v squared. And doing higher, okay, not foundation, you wouldn't have to apply these sort of questions. You would have to do the percentages, but not apply these equations to this problem. Okay, so 540. Now half of 40 is 20. So I'm just going to divide that by 20 equals v squared. But you will at high have to rearrange it and be able to find that velocity. So the square is on the other that side. So take it over to the other side. It becomes the square root. So 54. I'm going to cancel out those zeros over 2 square root equals the velocity, and that comes out to be the square root of 27 equals 5.2, and just pop the answer on the answer line. Okay, but we haven't finished, okay, because it's asking now use an equation from page 2 again to calculate the mean force against the motion. So if it's against the motion, that means it's a resistive force. So you are having to do work against these resistive forces, and that accounts to the energy lost to the surroundings. So if we know how much kinetic energy we've got, which is now 540, instead of doing the fraction again to work out 55%, we can just take away 540 away from 1,200 to get what the 55% is, which is the energy lost to the surrounding, which is the work done against the resistive forces. So the equation you want is the work done equals force times distance. That work done is the energy lost to the surroundings, okay, and that will be 1,200 take away 540, and that comes out to be 660. joules. Okay, so therefore employ now force times distance equals 660. You've got the distance because the resistive forces, they act over the length of the slide, which is 12 meters. So what we'll have is work done equals force times distance. So work done divided by the distance equals the force. So 660 divided by 12 comes out to 55 newtons, and then pop the answer on the line. Explain why energy is lost to the surroundings. Because you're doing work against resistive forces. So doing work against resistive forces. Now be specific, say what these resistive forces are and where are they. So friction is the resistive force here, and it's between the slide and the person. Do we need anything more than that? I think not. I think that is good. And if you wanted to kind of like relate energy to an energy, you can say doing work against resistive forces. So the energy transfer is from gravitational potential energy to kinetic energy and heat energy. So that produces heat energy or thermal energy. It doesn't matter which one you use. WJC like the word thermal energy, but heat energy will do just as well. Now, I would like to go on to this number 2, but before I do that, I've got so much I want to do, and I think I ought to kind of like show you this kind of written one, because this written one is kind of like, it's an essay question that came up a few years ago. And it kind of didn't get very many marks from pupils, all right, because of several misconceptions. And I'll go over that, and I'll show you what I mean by that. So the car is pulled to the top of the first peak at the beginning of the ride, but after that the car must complete the ride on its own, and every peak on the roller coaster must be lower than the one before it. So we've got to explain in terms of energy transfer. So the examiner is looking for the transfer of energy, not just stating that when it's at the top it's got gravitational potential energy, and when it's at the bottom it has kinetic energy. That's not going to be good enough. It might get you 1 mark, all right, okay, but it's been pulled up to the top, so it might actually have a little bit of kinetic energy as well as gravitational potential energy. You don't know, okay, because you don't know whether it's moving or not. So it could have some kinetic energy because the thing is moving, all right, plus gravitational potential energy. That gravitational potential energy at the top will be the maximum gravitational potential energy, but the total energy will be whatever kinetic energy it's got, all right, because it was moving maybe in the first place to get there. If it wasn't moving and it said it was stationary at the top there, then the maximum total energy that it's got is the gravitational potential energy. But just be careful because you're not being told. So as it comes down from the top to the bottom, the energy transfer is gravitational potential energy into kinetic energy. All right. And then when it gets to the bottom, it hasn't got a minimum gravitational potential energy, because that would have a minimum gravitational potential energy at this stage here at the very, very bottom. But here it's still got a height. So that tells me that there will be some gravitational potential energy as well as kinetic energy in the dip here. Then gravitational potential energy, kinetic energy at the bottom here will turn back into gravitational potential energy. They're interested in what the energy transfers are. Stick to the question, reread the question, highlight what they want from you and stick to that. Don't go off into forces. Stick to energy, but stick to energy transfers. Now you'll notice that this peak is lower. Now, if that peak is lower, then you know that energy cannot be created nor destroyed, only change from one form into another. So therefore, there must be something going on here. And indeed, perhaps it is because energy is being lost. So that might account for the fact that it's got a lower peak. So energy lost maybe to the surroundings, maybe to the track, because you're doing work against resistive forces. So work done against resistive forces. And that will be given by work done equals force times distance. Now, the resistive forces here, I would say the more important one would be the frictional force. So that would act over the distance of the actual ride. So we haven't just got the gravitational potential energy being converted into kinetic energy. We've also got now the kinetic energy into gravitational potential energy. And then because it doesn't go to the height that it was before, you've got energy being lost by doing work against friction. Okay, right. Now I have included there a mark scheme, and I have also included, and this comes from the WJEC question bank. So you can literally make your own questions. You can select to have the mark scheme, but you can also have, kind of like the report of the examiners. So the examiners mark so many, and then they kind of like put together their comments so that they can be sent back to schools to kind of like feedback to the pupils on how they're doing. And this kind of like shows you very often what the misconceptions were. All right, so for example, no potential energy at the bottom of the first peak when it was 50 meters high. There was no kinetic energy present at the first peak, but you haven't been told it was stationary. There's a confusion to say that gravity slows the car as it drops, but gravity stays the same. So, there is a confusion, and then not referring to the energy of the car being a combination of both potential energy and kinetic energy. All right, so showing that you have an understanding that you're looking at the total energy of the system. Okay, all right, so I think, how am I doing? I'm not sure whether to go to another question or have a look. Let's go and have a look at a sample of questions, because this is a different one. This is some of our pupils that have just taken their mocks, and this was one of their questions. They had to plot a graph of force against the length of the spring, and they were expected to draw a suitable line. Now they plotted, so I'm not going to go into the details of I just want to show you what a typical kind of like response looks like, and look at a few kind of like misconceptions. All right, now this pupil here, they've got 1, 2, 3, 4, 5 plots, and they've actually plotted those in the right place, and they've got their axes nicely so that the plots spread out over half of the graph grid in both directions. So this is really quite well done. Unfortunately, though, this candidate did not have a ruler, I don't think, and they kind of like assumed that the line has to go through the origin, which is a bit of a shame, because this is a nice example where the points kind of like all line up in a straight line. And I haven't got a ruler, but that will do. But please make sure you have a ruler. Please make sure your pencils are sharp, so that you don't get deducted marks for kind of like blobs and too thick lines. So you do need a ruler for this, and you need to what we call extrapolate that line. It says state the length of the spring when no force is applied. So that is down to this part here when the force is 0. So where does that line cross the axes here? All right, is what the length of the spring originally was, and you're expected to extrapolate and work out and what it was. And this candidate has done that, but they actually haven't drawn their line. So I actually doubt that they would have got that mark because it's not being, they're not using a straight line, and they've curved it as well. Now, this is again energy, but elastic energy. So we say work done stored to stretch a spring is the energy stored in the spring, and that's given by the area underneath the graph. But before I shade it all, the two spring system is stretched to a maximum of 15. Okay, so we've got to identify where 15 is in order to work out the area under that graph, which is given by work done half force times extension. So they've got the right equation, but look, I don't know that they've got the right, because look, 12, 16, go in between 14, so 15 is halfway between that, go all the way up to the line, and then you can shade the rest in. So that clearly goes up to 12. So this candidate has got it because they've got the 12, but they haven't got, so they've got the force of 12, but they haven't got the right extension. So they needed 15, and be careful here because the extension is given to you. They're told 15 times 10 to the minus 2 is given on the axes as well. So you'll have to kind of like obey these power of 10s and slot them in. Okay, so again, they've got the joules correct, but they haven't quite got that extension correct. Okay, now all of that elastic energy, okay, and I'm not even really reading the question, that elastic energy there, which we call work done in stretching the spring, elastic potential energy, is converted up here. The fact that I can see a velocity here means that it's going to be converted into kinetic energy. So the work done in stretching the spring is going to be converted into kinetic energy. So we can relate one to the other. Whatever you had, and this should be 0.9 here, you can put as the answer for the kinetic energy because it's all converted. So what's the assumption here? The assumption is all of the work done is converted into the kinetic energy gain. And then you can rearrange to find velocity, and we've done that before, so I won't waste time doing that. Then it says, explain why the actual launch velocity is always less. So there is an assumption that we made here that all of the work done is used to have a gain in kinetic energy, where in actual fact that kinetic energy will probably be less than what it really should be, the theoretical value, because energy is being converted into other forms, i.e. doing work against, and in this case it will be against air resistance. So energy is turned into heat energy. So now we can say that the assumption has to shift, so that the assumption goes from work done, i.e. the elastic potential energy, I'll put that in brackets, is equal to the kinetic energy gain plus the heat energy because you have done, or thermal energy because you have done work against a resistive force. So if you see all of that, that has got to stay constant in terms of the energy before is the same, but the kinetic energy would have to be less because some of the energy has been converted into heat energy. And then this last little bit, it says, suggests that the maximum momentum would be more appropriate than stating the maximum velocity. Well, this comes back to the lesson before, where we were looking at kind of like forces and Newton's second law. And Newton's second law can be known as F equals ma, or change in momentum over time. And if you look at it in terms of change of momentum over time, then you can get an idea of how big the force is, because you're taking into account not just the velocity, but also the mass to give you the momentum. For the same question, this candidate down here has clearly misplotted. I think he's probably not kind of like worked out his scales properly. His very common error, he's tried to force his line here through the origin, even though it's, you know, 1 square off, so it's not actually going through the origin. And actually the trend would be somewhere like here. And I wonder if this one is misplotted, but anyway, I'm not going to. 22, no, that looks right. 7, no, I wonder, it must be this one. Yeah, it must be this one that's misplotted. So my line would be a little bit more rotated. And here, can you see that the candidate here for this read off, this candidate has read it as 12.5 because they haven't looked at the first and the last of that kind of like square and then work out that this is actually 14. So this bit here would be 15. So they've misread their graph because of the axes. Okay, that's all I want to show you on this. And now I can go back to, I'm just wondering, whoever's watching, I can either go through more exam questions, or I can go on to vehicle efficiency and vehicle safety. What would you like me to do?
There's a slight delay, Miss Owens, but we'll wait to see if anyone pops it into the chat now, okay?
Yeah, okay. It's either vehicle efficiency, which is a little bit more theory, or I can work through this problem. And while they do, I will carry on writing.
Nothing in the chat, Miss.
Okay, all right. So I'll carry on with this one, okay, and I'll see if I get that far, okay? So the total energy of the car at A is given by, now look, this is the key, it's moving, it's got to have kinetic energy. The fact that it's at a height, it's got gravitational potential energy. So if the total energy of the system at the top will be both of those things, and look, they haven't told you to use an equation here. They're just expecting you to be able to do it. So mg change in height plus half mv squared. So the mass is given by 1,500 times by g is 10 times by the change in height 40 plus half of the mass again 1,500 times by the velocity at the top is given by 12 squared. Okay, and if you add both those up, I have done it previously and I think I'll just resort to it so that you don't have to waste time now watching me do that. So that comes out 7.
Mrs. Owen, if it's okay, we have had a student saying vehicle efficiency, please. So
yes, okay, that's fine. I'm happy to do that. Okay, yeah, I will do that.
I don't know if you just want to finish that bit you were on.
Yeah, I'll finish this bit. So for the car moving at 12 meters per second at A, calculate the maximum height that the car reaches before stopping at point B. So what we've got to assume is that all of this energy is the total energy, and that gets converted into gravitational potential energy. So you can say that 708,000 is equal to mg, the change in height, and then you can rearrange it. You know the mass, you know g, and so you can work out the change in height. But why doesn't it not actually reach that height? Because it gets converted into doing work against the resistive forces, i.e. friction along the track. Okay, so if I stop there and I go on to, have I done enough there? Probably not to get my mark, but I will. Okay, right. So now looking at vehicle design, why do we want to look into vehicle design for greater efficiency? Well, we want to improve the efficiency of vehicles because that means that we will use less fuel. We all know that the cost of fuel is rising all the time, so that if we can use less fuel, it means the journey costs less. And also it's better for the environment, but it's not good enough for you to actually say it's better for the environment in an exam question. You've got to say things like you're going to be burning less fossil fuels, so you're having less greenhouse gases, which cause less global warming. You've got to say the effect of using less fuel, what it will mean in terms of your pocket and in terms of the environment, but be specific. So the efficiency of a vehicle can be improved in many ways. We can reduce aerodynamic losses, okay, and that is called by streamlining designs. So we only have to look at the 1950s, 1940s for the shape of the cars then to the shape of the cars now. Cars are much more streamlined, they're curved, they've got spoilers at the back, they allow the air free passage around the car. So that means you're doing less work done against the resistive forces of the air resistance. Another thing to consider is to reduce the rolling resistance due to the friction between the tyres and the road. Notice they say what the force is, where it's happening, and what the name of it is. And in order to do that, what you want the tyres correctly inflated. Okay, so you got a safety issue here, because if it is over inflated, then you won't have that contact with the ground to give you the friction in order to cope with banking and going around circles. And if it is too low in pressure, the friction is too great and you get these rolling losses, so that you are again doing work done but against the friction between the tyre and the road. All right, so it's very relevant to what we have been looking at. Idling losses are due to the engine kind of like being on at a standstill. So if you've got a red traffic light and you're coming and you've approached it, you come to stop, but you don't actually physically turn the engine off, and to have to put a key to roll it on again, it literally, your foot comes off the clutch, the engine automatically stops, but then as soon as you put your clutch back in, the engine starts again, and that will reduce the amount of fuel that you are using whilst you're stopping at that traffic light, say. So it's called a start-stop system. And then inertial losses, well, look back to what is mass. Mass is inertia. It is that resistance to change in motion. So if something is a very, very high mass, then it has what we call a very high inertia, and the resistance to change in motion is very high. So if it is moving already, it's going to be really hard to bring it to a stop. So we can reduce these losses because you need a lot of force to bring a heavy object to a stop. You only have to look at the lorries that we've got on our roads, the logging lorries, kind of like packed lorries, to see that actually they need quite a lot of force to bring that heavy vehicle to a stop. And in doing so, you are using more fuel to do that. Also, to accelerate it, to get it going to a speed, you need more fuel to get it, because you're having to overcome more inertia. All right, and the way we do this to prevent inertial losses because of them cars having a mass is we use lighter materials. So we can use carbon fiber, we can use polycarbonate, we can use kind of like lighter, less dense objects as opposed to kind of like mild steel. And that will reduce the mass. And these are called inertial losses due to the fact of when you're accelerating and when you're decelerating. Because all of that energy is being converted into heat energy in the wheels when you're coming to a brake. All right, now, so that addresses the efficiency of a car. I'm wondering whether to have the last minute to kind of like just relate back to the previous session that we did 2 weeks ago on forces, and kind of like the forces and doing work relates to greater safety for vehicle design in terms of using seat belts, crumple zones, airbags. For crumple zones, what you're trying to do is you're trying to do work against a resistive force, i.e. deforming the substance. So all of that kinetic energy you want to turn into doing work, deforming the car, i.e. the bumper on the car, and not the people inside it. Take the energy away from damaging the person. Seat belts, and airbags, what you're trying to do, and crumple zones are all trying to extend the time it takes to bring the vehicle to a stop, and therefore decrease the acceleration or deceleration, and therefore decrease the force acting on it. So you're always trying to kind of either extend the time or increase the distance with which it comes over to a stop. So I'm going to come back to where we were originally. I think you can say that we've covered work done against a resistive force, kinetic energy, elastic energy, and gravitational potential energy. We've looked at equations for all of those. We've related one to another, but you've just got to look at the problem in front of you and work out what the energy transfers are going on. Okay, I think I must call it a day now, and I will pass you back to Mr. Rith, and thank you very much.
Brilliant, thank you, Mrs. Owen, and thank you for the questions in the chat. And that's the end of this session then, and we look forward to seeing you again soon. Bye bye.